السلام عليكم، نتمنى تكونوا بخير وعلى احسن حال، ومرحبا بكم في هذا التمرين في مادة الفيزياء والكيمياء المستوى الثانية بكالوريا، علوم فيزيائية، المسالك الدورية، خيار، انجليزية. فهذا التمرين كيندرج ضمن الامتحان الوطني لشعبة العلوم الرياضية لسنة 2017 استدراكية. نبدأ على بركة الله. Donc, part 2. Determination of the radius of the moon trajectory around the earth. Donc التمرين هذا كيهدف إلى حساب يعني شعاع يعني ديال trajectory مسار ديال القمر حول الأرض. So this part aims at determining the distance Earth-Moon based on both the study of the motion of the Earth around the Sun and that of the Moon around the Earth. In each case, the motion is in a frame of reference assumed Galilean. Okay, so we consider that each of the Sun, the Earth, and the Moon has uniform spherical mass. There is only one universal gravitational force acting on the Moon by the Earth, and there is only one universal gravitational force acting on the Earth. So given the orbital period of the center of inertia G of the Earth around the Sun is T is equal to 365.25 days. Donc هنا نساو باش يترجموها. So the orbital period of the Earth around the Sun معروفة عام. The orbital period of the center of inertia G prime of the Moon around the Earth is G prime is equal to 27.32 days. We assume that in the heliocentric frame, the path of the center G is circular. أنا كنتحدثوا على the Earth is circular of radius r, big R, is equal to 1.49 times 10 to the power 8 kilometers. So this is the distance from the Sun to the Earth. Distance Sun-Earth. Its center. Its center is the center of inertia of the Sun. So this is the definition of the heliocentric frame. In the geocentric frame, the path of the center G prime, the Moon, is circular. Its center coincides with G and of radius R. هنا R محدوش hence because the aim of this exercise is determining R. We denote big M, the mass of the Sun, small m, the mass of the Earth, and m prime, the mass of the Moon. And we take big M over small m equal to 3.35 times 10 to the power 5, the ratio between the mass of the Sun and the mass of the Earth. And as you can see here, the mass of the Sun is this time bigger than the mass. You need 100,000 times, 300,000 times bigger than that of the Earth. So question 1, define the geocentric frame of reference. So as we have seen in the course, the geocentric frame is a frame okay, so as you have seen in the course. So yes, so effectively the geocentric frame is this, okay? So whose origin coincides with the center of the Earth and whose three axes, okay, are pointing towards very distant stars. Okay, so choose which one of the following statements is true. So A, the gravitational constant is expressed in meters per second. So it's we don't know, so we need to check this out. So to do this, we need to do what is called dimensional analysis. So we are going to see, recall, as its name suggests, dimensional analysis is the analysis of the dimensions of the different physical quantities like length, mass, time, temperature, etc. Okay, so we define some fundamental dimensions, okay, which are the following. So L. So here's a way to memorize them. An easy way is to recall LM shan, like this, LM shan, and add J at the end. So L is the symbol of the dimension of length. Okay, so and the unit of length is m. So actually we are going to displace this, so to allow some space. So it's very important to distinguish between the unit and dimension. So this is the unit and this is the dimension. Okay, so for length the unit is meters. For mass, so M stands for mass, its unit is kilogram. For time, the unit is seconds. For the intensity of the current, the electric current, the unit is amperes. Here is not O, is actually theta, and it represents the temperature. The unit for temperature is Kelvin. N is the amount of matter, the unit is mole, and J is the intensity of radiation of light. Its unit is candela. And as you can see here, these units are the fundamental units with which you can express any unit for any physical quantity. Okay, so we are going to use this to determine the dimension of G. So to determine the dimension of G, we have to know an equation in which G is present. So for example, we know that one equation that comes to mind is the gravitational force, which is equal to G times MA, let's say MA, MB over R square. So this is the unit. This is the quantity I'm looking for. Okay, so G is equal to F times R square over MA times MB. So to express the dimension, so I put the physical quantity between brackets. So this means the dimension of the physical quantity. Okay, I put it here. So let's say X is a physical quantity. So if I put it between brackets, it means the dimension of the physical quantity X. Okay, so J is equal to, the dimension of J is equal to the dimension of this, which is equal to the dimension of F, the force, times the dimension of R, which is a distance, is length, so L square. Dimension of mass is big M, so M minus 2. And the dimension of F, okay, it can be expressed in terms of these, but its unit is Newton, so it doesn't get, okay, listed here. So I have to find an equation in which F occurs. So we know an equation. We know that from Newton's second law, F is equal to ma. So the unit of, the dimension of F is equal to the dimension of ma, which is equal to dimension of m is big M, mass, and the dimension of A is, the unit of A is meter per second square, which is L T minus 2. Okay, because the unit of mass is kilogram here, and the unit of acceleration is meters per second square. Okay, so replacing this, the dimension in this equation gives equal to m, L times L become L to the power 3, m with m to the power minus 2 become m to the power minus 1 times t minus 2. So this is the dimension of G, and the unit of G is kilogram meters, kilogram minus 1 meters cube second minus 2, which is not equal to whatever they have stated, yes, meters per second square. Okay, so A is false. Okay, so A false. Now B. So the acceleration of the center G of the Earth is tangent to the circular path around the Sun. So this is also false. Why? Well, because F, the force, the gravitational force that the Sun acts on Earth, is equal to mAg. So from this equation, I can see here that these two vectors, F and Ag, have the same direction. And knowing that F is centripetal, Ag should be also centripetal. So centripetal means that the vector is normal to the trajectory and pointing towards the center of curvature. So let me draw you a drawing, okay, so that this gets clear. Okay, so here's a drawing of what we have. So we have the Sun, we have the Earth orbiting the Sun. The center of the Earth is G. It orbits the Sun with a radius r, so the orbit has a radius r, and here's the Moon with a center of inertia G prime, and orbiting the Earth at radius r, and the mass is m prime. Okay, so regarding question B, which is false. So why? Because from Newton's second law, F is equal to mAg. So the force that the Sun applies on or that acts on the Earth, okay, is this. Okay, and we can see here that from this equation they are collinear. Okay, they have the same direction, and so we know that F is centripetal, meaning that it is normal to the trajectory and looking towards the center of curvature, in this case the center of the circle. Okay, so in this case, so the question was the acceleration. So in this case the acceleration is not tangent but normal to the trajectory. It's we say it's centripetal. Okay, so let's move to C. So C, the acceleration has the same direction for a uniform circular motion. So this is also false because the acceleration is constantly changing. Okay, the direction of the vector, acceleration vector, is always changing. Okay, so C also false. Why? Because A, the vector A, is continuously changing. Okay, so because it's a vector, the vector changes if it changes direction or orientation, okay, or magnitude. or three at the same time. Okay, so A changes direction. Okay, at different points of the trajectory, A has a different direction, so A changes continuously. That brings us to the last part. Okay, so the question was choose which one of the following. So ultimately D will be correct. So the velocity of the uniform circular motion of the planet is not dependent. It's not depending or do not depend. So it's an error here. So do not depend on the mass of the planet. So the velocity of a planet do not depend on the mass of the planet itself. So this should be true, and we can verify this. So D, is true. And to verify it, okay, we know that. So this is from the course. V is equal to G ms over R square root. So this is from the course. If you want, you can go back to the course. I have done a separate video of the course, and here we can see, yes, so V square is equal to G ms over R. Okay, so this is in the case of the Earth orbiting the Sun. So this is the mass of the Sun. So V is equal to the square root of this. Similarly, here we have a planet, okay, that orbits also the Sun. Okay, so V is the velocity of the planet, G is the gravitational constant, and ms is the mass of the Sun. So let's add this here. So mass of the Sun. So this means that the velocity do not depend on the mass of the planets. So it's true. So generally, this question, okay, choose. So okay, so you don't have to demonstrate why A, B, and C are false. You don't have to, but I just did it so that you learn new things, like for example dimensional analysis and other things. Okay, so just in yes. Let's move on. So 3, in the FERDI base UN, write the expression of the gravitational force between the Sun and the Earth. So this is quite easy. Question 3. So F, the force that the Sun acts on Earth, is equal to G times M times the mass of the Earth on divided by R squared, the distance between them two, along the vector n. So I've expressed the force in FERDI base. Okay, it's along the normal vector. Moving on. 4, applying the Newton's second law, show that the motion of the center of inertia G of the Earth around the Sun is uniform and circular. So we are going to repeat what we have seen in the course, showing that the motion is uniform and circular. So applying Newton's second law on G of Earth. So this gives me F of S on G is equal to m, the mass of the Earth, over times Ag, sorry. This gives me m over r square, which is equal to m Ag. And we're going to simplify with m, okay. So we're going to name this equation equation 1. So projecting equation 1 onto G U, this gives me 0 equal to m AG. So AU, which is in this case dVg over dt. So as a reminder, AU, the tangent component of the acceleration, is equal to dv over dt. So this is from the first lesson of Newton's of mechanics. Okay, so this means, so the derivative of the velocity is equal to 0, which means that Vg is constant, which means that the motion is uniform. Now, projecting equation 2 onto the vector Gn, or onto the axis Gn, gives me G times m over r, which is equal to Vg, or yes, Vg square over r, and we don't have r. Okay, so we can simplify by r here. Okay, so this gives me, so actually let's oh, sorry. So this gives me r equal to Gm over V square. Which is equal to a constant. G is a constant, m, the mass of the sun, is constant, and V is constant from our previous deduction. So if R is constant, this means that the motion is circular. We deduce from this that the motion is uniform, circular, and uniform, or we have a uniform circular motion. Next, question 5. Establish the relationship of the Kepler third law of the motion of the center of inertia G of the Earth around the Sun. So we need to demonstrate the Kepler's third law. So first of all, Kepler's third law is t square over big R to the power 3. So this is applied to the orbit of the Earth around the Sun, so with the radius big R. And the orbital period is t according to the subject. So this is equal to a k, which is equal to a constant. So this is the Kepler's third law, and we shall here demonstrate it. So we already have this equation, so we know that so from this equation, V square is equal to Gm over R. Okay, and So we are going to name this equation 2. And we know that V is equal to R omega. So R is the radius of the trajectory and omega is the angular velocity, which is equal to R 2 pi over t. Because we know that omega is equal to 2 pi over the period. In this case, is the orbital period of the Earth. So V square will be equal to R square 4 pi square over t square. And we are going to name this equation 3. So we have two expressions of the same quantity, which is V square, which means that 2 is equal to 3. This means that Gm over R is equal to R square 4 pi square over t square. So rearranging this equation gives me the following equation: t square over r to the power 3 gives me 4 pi square over gm. So 4 pi obviously is constant, g is a constant, and m is a constant. So all of this is equal to k, which is equal to a constant. So we have demonstrated that. Next, question number 6. Find the expression of the radius r, which is the radius of the orbit of the moon around the Earth, in terms of m, the mass of the moon, of the Earth, sorry, big M, the mass of the Sun, T, the orbital period of the Earth around the Sun, and T prime, the orbital period of the moon around the Earth, and R, the distance Sun-Earth, and calculate its value. So R in terms of M, big M, T, T prime, and R. So for this question, we are going to use the results of question 5, which is Kepler's third law. That's why they ask us to establish Kepler's third law. So we know that t square over r cubed is equal to 4 pi square over gm. So this is for the orbit of the Earth. And we are going to do the same thing for the orbit of the moon. So and similarly by applying, so in this case it's t prime square over r, small r to the power 3 is equal to 4 pi square over gm. In this case is m, the mass of the Earth. So we are going to name this equation 5 and this equation 4. So we don't have the exact value of g and m. I don't think so. No, we don't have the value of g. We don't have the value of m, and we don't have the value of small m. But what we do have is the ratio m over m. So for that, we are going to divide this equation by this equation. So equation 5 over 4 gives t square, t prime square, r to the power 3 over t square, small r to the power 3 equal to big M over small m. Okay, so g and 4 pi square get simplified. And from this, we can isolate small r, which will be equal to r times the cubic root of m over m times 2 t pi square over t. Okay, so you can pause the video and check for yourself this equation. Okay, so just some arrangements, and to just give you a reminder, so if r3 for example is equal to a, r will be equal to the cubic root of a. Okay, so this is what we have done here, and r is out of the square root because if you have a to the power 3, this cancel with the cubic root and gives you a, like this. Okay, so because we have r3, so this is the expression of r. Numerical application. So r is equal to big R, which is 1.49 times 10 to the power 8 kilometers. Yes, indeed, the distance between the Earth and the Sun is approximately 150 million kilometers. So r is equal to, sorry, so we don't have to input the so time square root, the cubic root of, so the ratio m over m, so I have the inverse, so 1 over 3, or yes, 1 over 3.35 times 10 to the power 5 times t prime square over t. I forgot the square here. T prime is 27, sorry, 0.32 square over 365.25 also square, and we are going to, yes, so calculating this gives 3.81 times 10 to the power 5 kilometers. So here I have not converted days in seconds because we have t square over t square, so the units gets cancelled, so I don't have to convert here. Also here the mass goes of the mass gets simplified by the mass, so here the ratio is unitless. So this is without units, so r has the same units of r. So here I have kept the value in kilometers, so r should be also in kilometers, hence the value. So we reached the end of this video. كنتمنوا تكون هذا الفيديو بالاستفادة، ونشوفوا ان شاء الله في فيديو لاحق.